Gilbert's theorem of zeros. So we first had the weak version of it, which says that if so weak Nullstellensatz so that means if I an ideal in k x1 to xn, which is a proper ideal, so not the whole of this polynomial ring, then its zero set is non-empty. So every ideal which is not the whole polynomial ring has indeed zeros. And then we were about to look at the strong form of the Nullstellensatz, which is supposed to be about the relationship between ideals and their zero sets, and in particular, what is the ideal of the zero set of an ideal as compared to the original ideal. And so in particular, we found that if so we had introduced an ideal I in a ring R called a radical ideal first, if I is an ideal in a ring R, the radical of I which is denoted, so I write it just as if it were a square root. This is just the set of all elements in the ring such that the power of that element lies in I. N bigger than 0 such that f to the n is in I. And an ideal is called a radical ideal if it's equal to its own radical. So if whenever it contains a power of an element, it also contains the original element. And now we wanted to show the strong form of the Nullstellensatz, which said the following. So theorem Nullstellensatz says that if I have any ideal, I ideal in the polynomial ring in n variables, then if I take the ideal of the zero set of I, so here the I has two different roles. So this is the ideal of, and this is our given ideal, but I think it can easily be distinguished, is the radical of I. That's precisely what the precise relation between ideals and zero sets is. So now we wanted to prove this. So we have seen that if I take the ideal of the zero set of I, this contains I, and it is a radical ideal. So thus, it contains the radical of I. Okay, we saw last time it's a radical ideal, and we had seen before also this statement is also completely obvious from the definition. So now we have to show the other inclusion, and that's rather non-trivial. So we take an element F on this side, and we have to show that it lies in the radical of I. So that means we have to show there exists a number n bigger than 0 such that f to the n is an element in I. One can already see that this cannot be particularly easy because this n somehow comes out of nowhere. So what does the n have to do with anything here? The proof somehow must provide us with this n. It doesn't seem to be, it's difficult to imagine how this can come to pass. And so we need to, in order to prove it, one needs a trick. And the trick is one wants to reduce it to the weak null Stellensatz in one variable more. So to produce some kind of ideal in one more variable whose zero set is empty, and then somehow deduce this statement from that. Okay, so use a trick, so apply the weak null Stellensatz. In one more variable. Obviously in a way which is somehow related to our original problem, otherwise it wouldn't be so useful. So we make a new ideal out of I. So first, to make it a bit simpler notationally, we know that every ideal in kx1 to xn is finitely generated, so we can write it down in terms of generators. So write I equal to the ideal generated by f1 to fr. Fi has some polynomials. Put an ideal J. So take the ideal generated by the self-same f1 to fr plus one more generator, which also involves one more variable. So I call this f f times t minus 1. Now supposed to be an ideal in the polynomial ring in n plus 1 variables x1 to xn, comma t. As I said, so obviously a polynomial in just the first n variables we can view as a polynomial in n plus 1 variables. It just doesn't depend on the last. So these make sense also here, and then we have this. And so first I said we wanted to apply the weak null Stellensatz, so we want that the zero set of this ideal is the empty set. So what is the zero set of this ideal in a n plus 1, positive n plus 1 variable? So if I have a point P, comma A in a n plus 1, where this is an element in a n, and this is 1, so just in K. So when does it lie in the zero set of J? So this thing lies in the zero set of J. Well, if all these equations are satisfied for it. The first are polynomials here, which are supposed to vanish, are just polynomials in the first n variables. So they just concern the coordinates of P. And as this is the ideal generating the zero set, generating I, this means it will vanish where I vanishes. So maybe I can, to make it a bit easier, I write X for zero set of I in AN. So this lies in the zero set of J if the point P lies in the zero set of I, which means in X. And we want also this equation has to be satisfied. So F of P times A should be equal to 1. Okay. Now, however, we know that F lies in the ideal of the zero set of X. F is an element in the ideal of X, thus, and P lies in X, so thus F of P is equal to 0. And so if F of P is equal to 0, there's no A such that F of P times A is equal to 1. So thus this is impossible. So there's no point PA in n plus 1 which lies in the zero set of J. So it follows that the zero set of J is the empty set. And now a simple reformulation of the Hilbert Nullstellensatz of the weak Nullstellensatz was that if the zero set of an ideal is empty, then it contains the element 1. So thus, F1 is an element in the ideal generated by F1 to Fr, Ft plus 1, minus 1. Oh, T, obviously. Now, we can write this. We have to write out what does this mean. We can write 1 as a linear combination of these polynomials with coefficients in kx1 to xn, comma t. So thus we have F1 is equal to G0 times Ft minus 1 plus sum from I equals 1 to R, Gi Fi, where the Gi are some polynomials in n plus 1 variables. Okay, so that's nice. But the obvious problem is, what does this have to do with what we want to do? I mean, we now have left the polynomial ring in which we were working, and we have found this identity, which seems to be moderately interesting, but it's not clear what it's good for with respect to our problem. But now comes, so what we actually need to do, we need to come back to the original ring kx1 to xn. So and we do this by going via the fraction field of this polynomial ring of kx1 to xn. There's a homomorphism from this polynomial ring to the fraction field. So we define the following homomorphism. Ring homomorphism from this polynomial ring in n plus 1 variables. So the field of rational functions in x1 to xn, so which was, we had seen last time, we had defined as the field of fractions of polynomials in x1 to xn by doing what? If I have any polynomial, so g is a polynomial in x1 to xn and t, we send it to the same polynomial where we keep the xi the same, but the t is replaced by 1 over f. So the same polynomial g of x1 to xn. So this f is a non-zero polynomial. This makes complete sense. And this obviously is a ring homomorphism. If you add the two polynomials, then you will add what you get here. If you multiply two polynomials, you will multiply here. So it's clearly a ring homomorphism. So now we want to see what this ring homomorphism does to this formula here. And, and that will lead to the proof of our result. Always we'll send 1 to 1. But let me see. So the Fi do not depend on t, obviously. So if I do this thing, they are just sent to themselves. Thus, phi of Fi, Fi. What happens to this ft minus 1? If I take phi of ft minus 1, this is f divided by f minus 1, which is equal to 0. So this particular thing is sent to 0. So thus we get the following. Identity. So thus we get the following identity in this field of rational functions, namely that 1, obviously 1 is sent to 1, is equal to, the first term is not there because this factor is 0, sum I equals 1 to r, phi of gi times fi. Okay, so we found this identity. Now we are done. We will be done once we understand what this phi of gi is. I mean, what we can say about it. And the point is that the only thing we are doing here is replacing t by 1 over f. This will be a rational function whose only denominator can be a power of f. And then we will pull f to the other side and we'll get our result. So only, so as, so denominators in phi of gi are powers f. So some power f to the n of f. So let me just do it explicitly. So if gi is equal to say, sum ai1 to in and then j, x1 to the I1 and so on, xn to the in j, then t to the gi is the same sum, the same coefficients, and this also stays. And then the last one is divided, so I could say, if I write it like this, divided by f to the j. And this is a finite sum, so I can take the highest power that comes out, and so this will be of the form, so is of the form say gi divided by f to the ni, where gi is a polynomial in kx1 to xn. And then we put n, and this is remarkably the n that we wanted here, to be the maximal of these ni. And then we have, if we now write f to the n, this is by this equation here. So I multiply by this was divided by, so gi is equal to this. So this is sum, so phi of gi is equal to this. So this is the sum I equals 1 to r, gi times f to the n minus ni times fi. So these are all polynomials now in kx1 to xn, and they are all multiples of fi. So this is an element in the ideal generated by f1 to fr, which was our given ideal I. And that proves it. So that's a quite nice trick, quite roundabout way to get there, but in the end we get in this way this statement that if the ideal of the zero set of an ideal is the radical of the original ideal, and here we get this. Okay, so this was the so. So this is somewhat more difficult proof than we have seen before, but it's just nicely. It's also a rather pretty argument. I just want to give one very easy corollary, although I have to cheat a little bit, but I use something that we haven't done. So if I have an irreducible polynomial, as a polynomial, so it's not a product of two non-constant polynomials, then the zero set of f is irreducible. So this doesn't quite follow from what we did in algebra. I have to use some result which I didn't show. So the statement is that k x1 to xn is a unique factorization domain. You don't really need to know what that means. I mean, it means that, but in particular, it means that if you have an irreducible element, then the ideal generated by it is a prime ideal. So as f is irreducible, we have that f is a prime ideal. And now, if you look at the definition, prime ideals are automatically radical ideals. No? Because radical ideal means that whenever the ideal contains a power, it contains the original element. Prime ideal means more strongly whenever it contains a product of two, it must contain one of the factors. And then this with the power follows immediately. And so is a prime ideal, and thus also the radical ideal. And so thus it follows that the ideal of the zero set of f is equal to f, because it was already by itself a radical ideal, and it is prime. So thus, zero set of f, which is the same as the zero set of f, is irreducible. That's quite simple. There might be easier ways of doing anyway, but that's how it is. So this was, for the moment, as much as I wanted to say in the first pass about affine algebraic sets and affine varieties. Now we want to look at the case of projective varieties. Somehow very similar, but let me kind of motivate this by some analogy to some kind of differential geometry or topology. So affine varieties are like maybe, so let's say one would work over the complex, or say over the complex numbers with the usual analytic topology, then affine varieties like affine space would not be compact. And so that has a number of disadvantages because compact spaces are very nice. One can do many things with them that one cannot do with non-compact spaces. And so, in some sense, one would like to compactify them. And this is done by looking at projective varieties. So somehow you have something which is called projective n space, which can be viewed as a compactification of affine n space, and affine varieties can then be compactified to projective varieties. They will, and then they have some much nicer properties than affine varieties for many purposes. Again, obviously, one wants to do algebraic geometry, so one can also view them as zero sets of polynomials in projective space. One only will have to always use homogeneous polynomials. So now let me try to carry this out. So first I have to tell you what projective space is from this viewpoint, although I'm pretty sure you had it in differential geometry or topology in some form. Definition. So on, say, kn plus 1 without the origin, so we have an equivalence relation. Namely, an n-tuple A0, so An is equivalent to lambda A0 to lambda An for any non-zero lambda in K. Okay, so this gives us an equivalence relation. You could also think of it, if you have a point in this Kn plus 1 without 0, this will determine a line, one-dimensional linear subspace, through the origin, and they define the same linear, one-dimensional linear subspace if and only if they only differ by multiplying by a non-zero constant. So you can also view I maybe should also say the equivalence, maybe I will say this in a moment. So this quotient we call projective space. So the quotient set which I call Pn, which is Kn plus 1 without 0 divided by this equivalence relation, is called n-dimensional projective space. Okay, and as I just said, we can view it, can also be viewed as a space of lines, so space of one-dimensional linear subspaces of Kn plus 1. So this is a kind of coordinate-free description of this thing. Because, as I said, any non-zero vector in Kn plus 1 will determine such a one-dimensional linear subspace, namely the one generated by it, and two such vectors define the same one-dimensional subspace if they differ by a non-zero, by multiplying by a non-zero constant. Right. This is projective space. Maybe I will just some notations so that we have them once and for all. So the equivalence class of a point E0 to An in Pn is denoted, well, I don't use a standard notation because I can't do this well on the blackboard. I use the square brackets. So the standard notation is that you use round brackets and you put colons between them. Somehow, I don't find that very convenient on the blackboard. So I write it like that. and the AI are called the homogeneous coordinates of this point here. Point equal to AN. Okay, so these are just these words that we want to use. And now I want to briefly say how this is related to AN. I somehow said it can be viewed as some kind of compactification of a fine n space. So it should, in some sense, contain AN as a subset. So, in fact, it contains it in many different ways. But so Pn is the union of n plus 1 subsets, which are all bijective in a natural way. So AN. So what is it? So I write put I to be set of all the points, say A0, so AN, Pn, such that the ith coordinate is non-zero. The claim is that this is a natural bijection to AN. So for I n. So then the map I from UI to AN, which sends point A0 to AN. So, just I divide everything by the ith coordinate and throw away the one that I get when I divide AI by AI. So this is A0 divided by AI, 1 divided by AI, and then at some point I would get AI divided by AI, which is 1, but this symbol means that I don't have it. I delete that coordinate, and then it goes on until AN divided by AI. So this is a well-defined map, obviously, because AI is supposed to be non-zero. And this makes sense for the equivalence class, because if I multiply everything by the same constant, this still stays the same, because I divide and multiply by the same constant. So this is a bijection. And I can easily say what the inverse is. So from, say, small ui, from AN to UI, sending a tuple in AN, which I call B0, to Bn. Well, that wouldn't quite make sense because it's n plus 1, but I somehow just throw away the ith. So the n components, the one with the index I is not there, and this is sent to the element in projective space, where I have the same B0 until Bi minus 1, and for Bi I put 1, and then until then I get everything until Bn. And you can see that these are inverse to each other. And so these are bijective to each other, as if you understand the notation. So you start with A0 to n, then you get these quotients. And this in particular, if you take this and then go back, and AI was not 0, you get the vector, which is A0 divided by AI, A1 divided by, and so on, until then here you get 1, and then you get this. And so which is precisely, so you get this. And this obviously is the same vector as your original vector, because you have just divided by the non-zero AI. Okay, so this is this. So this is, I think you had this in some form in most likely either in topology or differential geometry, because it would be, this would be also what one uses as a chart if one wants to show that projective space, say over the complex numbers or the real numbers, is a manifold. So we want to use this map U0, or U0, from AN, large U0, to identify AN with U0. So practically, this means we identify a point A1 to AN with the point in projective space, which is 1, A1 to AN. Okay, and that, seems something I think one can do safely and doesn't feel very difficult to keep track of. So we just add the 1 at the beginning and make it a point in projective space. So if we do this, identification, we have that Pn is equal to AN union whatever does not lie in AN, so Pn without U0, which I write the hyperplane H infinity, where the hyperplane at infinity, which is just Pn without U0, can also be described as a set of all A0 to AN in Pn, such that A0 is equal to 0. So this is called the hyperplane at infinity. So if we make this identification here, it means that looking at projective space, we have added all these points to AN. They lie in a suitable sense at infinity, as we will see. So for instance, in case for n is equal to 1, we therefore have, we get that P1 is equal to A1 union the corresponding hyperplane at infinity, but the hyperplane at infinity is just one point, so I can call this union, can call this point infinity, and with infinity being the point 0, 1. So it's by itself all 0, A, but obviously these are only up to multiplying constants, so it's just 1.01. So for P1, we just add 1 point to A1. For n equal 2, we can say that P2 is equal to A2 union what I could call the line at infinity. Which which is just what I have here, but now it's just a set of all 0, A1, A2. Okay, so this is this description. So this is just projective space. Obviously, that's not what algebraic geometry is about. We want to consider projective algebraic varieties, which will be zero sets of polynomials in this projective space. And they better had something to do with the zero sets of some corresponding polynomials in a affine space. If everything is supposed to be connected to everything. So so we want projective varieties, projective algebraic sets of sets of polynomials. On this projective space. And on this projective space, we have these n+1 coordinates. So in k x0 to xn on Pn. Now, if we do this, there's immediately a problem, namely that it doesn't really seem to make sense. Namely, a polynomial does not define a function on Pn. F in k x0 to xn does not define. Unless it's constant or the zero polynomial or something. Because in general, we have, if we take f of a0, so I mean, how should the polynomial define a function? You just put the coordinates, the homogeneous coordinates of the point into the polynomial, and this should give us a function. So if I take f of a0 to an, this is usually not equal to f of lambda a0 until lambda an. And so this seems to have been a bad idea, but it's not quite as bad as that. For one thing, we don't really need our polynomials to be functions. We only need to know what their zero sets are. So we only need to be able to say when a polynomial vanishes at a point in projective space, not what the precise non-zero value is if it doesn't vanish. And then even that wouldn't work with any polynomial, but if the polynomials are homogeneous, then that makes sense. And so let me try to write this down. So but if G x1 to xn, x0 to xn is homogeneous of degree d, then we have, it's easy to see that if I take G of A0 to AN, so no, G of lambda A0 to lambda AN, this will be lambda to the D times G of A0 to AN. Just if you take any monomial of G and you put lambda, so which has degree D, and you put lambda A0 until lambda AN into it, then this is lambda to the D times taking the same monomial and put A0 to AN into it. This is true for all monomials, and so it's true for the whole polynomial. Okay, and so it makes sense to say that G is 0 at a certain point in projective space, namely if and only if it's true for 1 and equivalently for all representatives of that point in A0 to N. So in particular, we have G of A0 to AN is equal to 0 if and only if of A0, of lambda A0 to lambda AN is equal to 0 for all lambda in K without 0. And in that case, we will say that is our point P equal to A0 to N in Pn is a 0 of this polynomial. So, definition. Point 0 to AN in Pn is 0 of polynomial f. So I should maybe, yeah, I forgot something. So this goes before, or let G in N homogeneous of degree D. So in that case, a point is 0 to N. In N is called a 0 of G G of A0 to N. 0, and this is independent of the representative. Of the representative. Okay. And so, and in that case, we just write, and we just write G of P is equal to 0. So note that G of P itself doesn't make sense, because if I replace if I multiply all the coordinates by a constant, I get something else. But that G of P is equal to 0 does make sense, and that's what we do here. So now we want to define projective algebraic sets as 0 sets of polynomials, and obviously of homogeneous polynomials. So let S k x0 to xn set of homogeneous polynomials. So the projective zero set of this thing is, I denote just right, Z of S. Well, this is obviously just a set of all P in Pn, such that f of P or f in S. So the definition here, this makes sense. And sets of this form are called projective algebraic sets. Subsets of Pn of this form are called projective algebraic sets. And I mean, obviously, I will also write something, of F1 to Fr instead of set of these. No. Writing. And if f is to have just one polynomial, we call it a hypersurface. So Z of f, or say f homogeneous of degree d, called a hypersurface of degree d. Okay, so these were just these definitions. And now, just to be on the safe side, at some later point, we will sometimes want to use the zero sets both of the same polynomials, both in the affine and projective space, and we want to distinguish. So if, well, maybe yeah, okay. If we need to distinguish between the projective zero set say in Pn and the affine zero set in say an plus 1, because we have n plus 1 variables, we call the first, so this is called say of S, and this is denoted A of S. But we will see this, use this a little bit towards the end of this section when we talk about the projective Hilbert-Nurstein sets. So mostly now we are doing projective geometry, and when we write Z of S, the zero set is meant in projective space. So let me give a few examples. They're not very examples. So So for instance, the empty set, which is the zero set of the polynomial 1, which is homogeneous of degree 0, and n, which is the zero set of the empty set of polynomials, are projective algebraic sets. So I call a hypersurface one called a hyperplane. Zero set of polynomial of degree 1. So that just means it corresponds, before taking the equivalence classes, to a one codimensional subspace of Kn plus 1. And so, in particular, this hyperplane at infinity is a hyperplane. Namely, it is just the zero set of the polynomial x0. The hyperplane. Otherwise, called it the hyperplane at infinity. Maybe I can also talk a bit about this compactification business. So one of the things is that in Pn, any two lines, so which means, so say in P2, any two lines, which means any two hyperplanes in P1, will intersect. And obviously, if this corresponds to lines in A2, then the intersection will happen at infinity. So let's look at, so if I look, for instance, if I look at the lines z of x1, and say z of x1 minus x0. So these are two lines in P2. I could look at the intersection with A2, where by this I mean I intersected with U0, and then I identify the point 1, so and so with this. So their intersection with A2 is, so the point to get to, I mean, if you look at this operation here, what you just do is you put you put x0 equal to 1. So their intersection, the first one is the zero set of x1 in A2. And the intersection of this one is the zero set of x1 minus 1 in A2. So these are just two parallel lines. So one is x1 is equal to 0, one is x1 is equal to 0, to 1. So we get these two parallel lines. So 1, 0, and 1. And obviously they don't intersect, they go on to infinity. But in P2 they intersect, so somehow there's some kind of perspective that they will somehow intersect on the line at infinity. They have an intersection point, namely clearly the intersection point is in the point 0, 0, 1. Because here, if x1 is equal to 0, x1 minus x0 is equal to 0, so x0 is equal to 0. So we have x1 and x0 are equal to 0. So these two coordinates are 0. And then, as everything is only up to multiplying constants, we just get this one point, which lies on the line at infinity. So here, so these two lines, if I kind of complete them in the projective plane, they do intersect in a point. In fact, it's an easy exercise that any two lines in P2 will intersect in one point. I mean, unless they are equal, in which case, I mean, they are equal. Intersect in very many points. Okay, so now we have talked about the zero sets of, so affine algebraic sets as zero sets of some polynomials. Now, we want to, so the theory is very similar to the affine case. So in the affine case, the next thing is that we wanted to say that every affine algebraic set is a zero set of an ideal. And so we want to say the same here. But we have to be a little bit more careful, again, because we had to restrict our attention to homogeneous polynomials. So we have to deal with special kinds of ideals, which are called homogeneous ideals. So definition. First, so if I have any polynomial f n, we can write it as a unique way as a sum of homogeneous polynomials, each of different degrees. So it can be written sum f is equal to, say, f0 plus f1 plus, and it stops at some point, namely at the degree of the polynomial, where each fi is homogeneous of degree d. Now, obviously, we just of degree I, obviously. Obviously, we just collect all the monomials of degree I in F together with their coefficients and sum them up, and this gives me Fi. And so these things are called the homogeneous components of F. An ideal will be called homogeneous whenever, with every polynomial, it also contains all its homogeneous components. I, k, 0 is n, is called homogeneous if for every f in I, it also contains all homogeneous components. See Fi of F. Okay, so that's one way of seeing it, but there's also another way of describing it, which is quite simple. Namely, an ideal is homogeneous if and only if it is generated by homogeneous polynomials. if and only if I is generated by homogeneous polynomials. That's a quite simple fact. Maybe I will still prove it the same. So obviously there's if and only if, so I have two directions. Assume the ideal is homogeneous. So assume I is homogeneous. So it will somehow be generated by some elements. So let F alpha be a set of generators. I could actually then I can just take all the homogeneous components of all the elements. Then F alpha I, and now let alpha and I run to all possibilities, are a set of homogeneous generators. No, they are obviously homogeneous because I've taken the homogeneous components, and I know that if the ideal contains any polynomial, it contains the homogeneous components, so the ideal will contain these homogeneous components. And obviously, if you have all these elements, you just take the sum over all I, you get F alpha, so you get the generator, so these also will generate. So this is the direction, but the other direction is not much more difficult. So assume that I is generated by homogeneous elements. So say polynomials. Alpha. So then we can write any element f in I as a combination of this with coefficients in kx1 to xn. So every f in I can be written f is equal to sum ai alpha I, where the ai, so a finite sum, where the ai are elements, are some polynomials in K. I want to have my polynomial ring is still x0 to xn. Okay. Now, so the G, but these things are homogeneous. So as alpha I is homogeneous, the part of degree, the homogeneous part, of degree, say, d of ai times g alpha I is just, so it's just the part of ai of degree d minus the degree of G alpha I times G alpha I. No, this already is homogeneous, so the degree adds up like this. So thus, get that the homogeneous part of degree d of f is just the sum over all I, ai, the part of degree d minus the degree of G alpha I, G alpha I. And so this is also it's also in the ideal, because it's in the part generated by this G alpha I. So, yeah. Okay, so that was the simple fact. So therefore so using this we can talk about the zero sets of ideals, of homogeneous ideals. Again, I'm slightly careful by what we so for the definition for an ideal I in a homogeneous ideal, so I subset k 0 to xn ideal. So the zero set of I is not precisely what one would think. So this is the set of all p in Pn such that f of p is equal to 0. Well, we haven't said what it means for a general element in a ring, but we know in the polynomial ring, but we know what it means for homogeneous element. So for all homogeneous f in I, okay, to require that all homogeneous polynomials vanish. And we can also talk about the homogeneous ideal of some subset of Pn, which is just the ideal generated by all homogeneous polynomials which vanish on this subset. So for x in the subset, the homogeneous ideal I of x, so of x is Ix. The idea generated by all f in k 0 to xn such that f of p such that f is homogeneous and f of p is equal to 0 for all p in x. Okay, so we see that everything is extremely similar to the defined case, only that we have to sometimes, at the appropriate places, throw in the word homogeneous to make up for the fact that polynomials are not functions on Pn. Now, after making all this story, I will now tell you that it actually wasn't really necessary. I could also have talked about the zero set of any polynomial and defined this in a different way, but it's for some other reason not convenient. So let me just make this as a remark. The exercise to see the following. If F is not necessarily homogeneous, we could define so f of p is equal to 0 if and only if f of a0 to an is equal to 0 for all representatives of p. So if and only if f of a0 to n is equal to 0 for all to n. Now, we could make such a definition, and that makes sense. So, however, so the thing, what is in some sense the disadvantage of this is the following. So, why one doesn't do that? One can see that if you have one polynomial, it actually gives you many equations. So it's as if you just write down one non-homogeneous polynomial and it gives you many conditions at the same time. It's just very confusing. So f of p is equal to 0 with this definition. If and only if fi of p is equal to 0 for all I. So in some sense, if I give one non-homogeneous polynomial, it's the same as if I give you many homogeneous polynomials, and all of these conditions have to hold. And that's somehow not the right way to think of it. You would think if you put one polynomial, it gives you one condition and not whatever, 50 conditions. On the other hand, if we make this definition, with the definition star, we do get that if we have a homogeneous polynomial, that the zero set of I that I have defined here can also be just described, also just a set of all p and pn such that f of p is equal to 0 for all f in I. So for homogeneous polynomials, if you choose this slightly crazy definition, we get this. And also the ideal of x will then just be the set of all polynomials f in kx 0 to xn such that f of p is equal to 0 for all p in x. But there are really good reasons not to use this definition and insist on homogeneous polynomials. Okay, so time is almost up. Let me see. So can maybe briefly talk about the risky topology. So as you maybe notice, we are kind of step by step, kind of retracing our steps. We do precisely the same thing that we did for affine algebraic sets, for projective algebraic sets, only, with a slightly different language. And we show that in a suitable sense, all the results we proved for affine algebraic sets are also true in the projective case. So the next thing is that there is a Zariski topology on Pn whose closed sets are the projective algebraic sets, and that every subset of Pn carries, will be given then the induced topology, which we call the Zariski topology on Pn. So first, I will repeat or just state some properties of, how projective algebraic sets behave, which have the same proof as in the affine case. So with minor modifications as in the affine case, we have the following proposition. Many, but okay. They're all elementary properties. So first, so this is now if say X is contained in Y in Pn, then it follows that the ideal of X contains the ideal of Y. This is obvious from the definition. Then, in the same proof as in the affine case will show if Y in Pn is a projective algebraic set. Did I actually say that? Yeah, I said that. So is a projective algebraic set, so a zero set of some homogeneous polynomials. Then if I take the ideal of Y and take its zero set, then this is again Y. No, we had seen this. Then as in the affine case, if we take a homogeneous ideal, K in K x0 to xn, and we take the ideal of the zero set of J, then this will at least contain J. And this is also directly obvious from the definition as in the affine case. And if we have two sets of homogeneous polynomials, if S is contained in T, and these are in K x0 to xn, and these are homogeneous, then obviously the inclusion of the zero sets is the other way around. And we also have that every projective algebraic set is a zero set of an ideal, namely if S is a set of homogeneous polynomials, then it follows that the zero set of S is the same as the zero set of the ideal generated by S. So in particular, every projective algebraic set is a zero set of a homogeneous ideal. Okay. And now we come to actually things having to do with this Zariski topology. So if I have a set of homogeneous polynomials, so for a family S alpha of sets of homogeneous polynomials in K, say x0 to xn, have that the zero set of the union over all alpha S alpha is the same as an intersection over all alpha of the zero set S alpha. This is essentially a tautology, no, because we have the condition that all these when we look at the points where all these polynomials vanish, which is the same that we look at the intersection of the locus where any of them vanishes. Okay. So, and seventh, let S and T okay, x0, xn be sets of homogeneous polynomials. Then, if I take the zero set of S times T, so just all the products of one element of S and one in T, obviously these products will also all be homogeneous, because the product of two homogeneous polynomials is homogeneous, is the same as the zero set of S union the zero set of T. And this is also quite obvious, and anyway, it's obvious in the same way as it was in the affine case. So the last two say obviously that arbitrary intersections and finite unions of projective algebraic sets are projective algebraic sets. And so this allows us to define the Zariski topology. So we had already seen that n equal to the zero set of the empty set of polynomials, and now the empty set, which I now could also view as the zero set of the whole polynomial ring as a homogeneous ideal, are projective algebraic sets. So if I can make a topology where the closed subsets are the projective algebraic sets, and that's called the Zariski topology. So the Zariski topology on Pn is the topology closed subsets are the projective algebraic sets. Okay. And any subset of Pn is given the induced topology. So we also have Zariski topology. Okay, maybe I can, so we also have Zariski topology on projective algebraic sets. And an open subset of a projective algebraic set we will call a quasi-projective algebraic set. It's just how it's called. So an open subset algebraic set called quasi-projective algebraic set. I cannot help this slightly complicated name, that's how they are called. And so in particular, if we do make the identification, we have that, so with identify an to u0 in Pn, we get that an and in fact any fine algebraic set are quasi-projective algebraic sets. Okay, so maybe that is enough for now. On Wednesday I will tell you a bit more. I will then also do the decomposition into irreducible components and the projective version of the Nullstellensatz, and then we will go to the next topic, which is kind of what would be the homomorphisms between fine and projective varieties. So maybe I stop here. Are there questions or comments? You're here. Yep. Okay. If not, I wish you a nice evening, and we see each other. Yeah, and we see each other on Wednesday.
Thank you. Bye.
Bye.